For an example of making use of the area formula, I'd like to solve the following triangle and find its area. So the triangle that we have here is A is 9, B is 5, and C is 8. I've given you all three sides of the triangle, so this would be considered the side-side-side case. The approach to use for the side-side-side case is we're going to start by using the law of cosines to determine one of the angles, and we might as well go for the biggest angle. I'd like to find alpha. So use law of cosines to find alpha, which means that we'll need the version of the law of cosines that contains an alpha. That's the one that starts with a squared. So a squared is equal to b squared plus c squared minus 2 times b times c times the cosine of alpha. Let's plug in all the things that we know. This will be 9 squared is equal to 5 squared plus 8 squared minus 2 times 5 times 8 times the cosine of alpha. In case you haven't already done so, having a calculator handy for this problem is going to be crucial. So, be sure that you have yours handy. Simplifying each of these, we'll get 81 is equal to 25 plus 64 minus 2 times 5 is 10 times 8 is 80 times the cosine of alpha. Combining our like terms together, 81 is equal to, let's see, that'll be 89 minus 80 times the cosine of alpha. Subtracting 89 from both sides will give us negative 8 is equal to negative 80 times the cosine of alpha. Dividing both sides by negative 80 and reducing, we'll get 1/10 is equal to the cosine of alpha. Applying an inverse cosine will give us the value of alpha. This is where the calculator is going to come in handy. So the exact value would be the arc cosine of 1/10. The value that we're looking for is going to be, make sure that the calculator is over in degree mode, the inverse cosine of 1/10, close those parentheses. So what I'm going to do here is round my answer at the second decimal place, but hold a couple extra decimal places just in case. And we'll call that 84.26, and then we'll put a little 0.8 right after it, degrees. Now once you have this angle, if you'd like to use the law of sines to find another angle, that'll be fine. If you want to reuse the law of cosines, that'll work as well. So what I'm going to do is now use the law of sines to find the smallest angle. Smallest angle in this case is going to be beta, due to the fact that that corresponds to the smallest side. Now that of course means I'm going to need the version of the law of sines that involves beta, and I'm also going to need the version that involves alpha, since that's what I just found. So sine of alpha over A. Now for the purposes of what I'm doing here, I'm going to revert back to the exact value. So sine of beta over B, which is 5, is equal to the sine of alpha, which is the inverse cosine of 1/10, over A, which is 9. I'm then going to multiply both sides by 5 to get that the sine of beta is equal to 5 times the sine of the arc cosine of 1/10 all over 9, and finally take an inverse sine of both sides. So we'll get that beta is equal to the arc sine of the sine of the arc cosine of 1/10. Oh, coefficient of 5 up there as well. That's all over 9. Now that seems like a great idea to plug into the calculator, or a great time to plug everything into the calculator. So inverse sine of 5 times the sine of the arc cosine of 1/10. Yep. Divided by 9, close parentheses. Whoosh. So beta is going to be about 33 point, we'll call that 55 with a little 73 right after it. Once you have two angles, there's really just one way to go to find the third angle, which is going to be to subtract from 180. So gamma is going to be 180 degrees minus alpha minus beta. Now for this, I'm going to go ahead and use the rounded to 2 decimal places versions. So that'll be 180 degrees minus alpha, which was 84.26 degrees, minus beta, which is 33 point, if we round appropriately, that'll be 33.56 degrees. Plugging that all into the calculator, 180 minus 84.26 minus 33.56 gives us 62.18 degrees. Now, in addition to all of this, we're also supposed to find the area of the triangle. Now, in my mind, it makes the most sense for us to use the side, 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 or Heron's formula. So for the area, we'll use Heron's formula. What we'll do is, after we use Heron's formula, we'll go ahead and approximate it using one of the angles as well, just to make sure. So semi-perimeter is going to be the perimeter divided by 2, which is equal to 9 plus 5 plus 8 all over 2. The perimeter, if I add all of that up, we'll get 22. So the semi-perimeter is going to be 11. According to Heron's formula, this is going to be the semi-perimeter times the semi-perimeter minus A, the semi-perimeter minus B, and the semi-perimeter minus C. So we'll get 11 times 2 times 6 times 3. Now if you're interested in the exact value, 6 times 2 times 3 is 36, and the square root of 36 is 6. The 11 sticks around. So 6 square roots of 11, or if we approximate that in the calculator, 6 square roots of 11, ooh boy, we'll call that just about 19.9, rounding up the first decimal place, or the second, or the third. Wow, that's really close. Now, just for the sake of making sure that they work, I can grab any of those 3 angles that we had from the previous and use the side angle side formula. For example, I could say that the area is equal to 1/2 times A times B times the sine of gamma. Copying those values from the other sheet of paper that I have right next to me now. A was 9, B was 5, and what we got for gamma right at the end was 62.18 degrees. Let's go ahead and toss that into the calculator and see how the results match up. So 1/2 times 9 times 5 times the sine of 62.18. I'm hoping, fingers crossed, that we are going to get 19.9. And we do. That is fantastic to see. Now you'll notice that once we get out to about the 4th decimal place, there's a little bit of error in our approximation, and that's because gamma was a rounded angle anyway. So let's just go ahead and say approximately equal to, just for the sake of, consistency.